Have you ever had that feeling where a boring afternoon drags on forever, but a fun night out seems to vanish in a blink? We usually think of that as just a psychological trick, a matter of perception. We assume that time itself is a steady, relentless drumbeat, ticking away at the exact same rate for everyone, everywhere in the universe. For most of human history, that is exactly what we believed. Isaac Newton, one of the smartest people to ever live, described time as absolute. He thought of it as a master clock for the cosmos, independent of anything else. In that view, 1 second on Earth is exactly 1 second on Mars, or 1 second in a galaxy billions of light years away. But here is the unsettling truth. Newton was wrong. Time is not a constant background stage where events happen. Time is flexible, it stretches, it squashes, and most mind-bending of all, it depends entirely on how fast you are moving. If you were to get into a spaceship right now and accelerate to 99% of the speed of light, you would literally break your synchronization with the rest of the universe. For you, a few minutes might pass. For us back on Earth, years would roll by. This isn't science fiction. It is a measurable, proven fact of our reality called time dilation. But why does it happen? Why does the simple act of moving fast force the universe to slow down your personal clock? To understand this, we have to stop thinking about time and start thinking about light. Imagine you're standing on the side of a highway. You watch a car drive past you at 60 miles per hour. Now, imagine you get in your own car and chase after it at 40 miles per hour. From your perspective, that first car is now only pulling away from you at 20 miles per hour. This is how we intuitively understand speed. Velocities add up and subtract. If you run forward and throw a ball, the ball moves faster. If you run backward and throw it, it moves slower. In the late 1800s, physicists assumed light worked the same way. If you were moving toward a light source, the light should hit you faster. If you were running away from it, it should hit you slower. But when they actually measured it, they found something impossible. No matter how fast they moved or in what direction, the speed of light was exactly the same. It was always 299,792,458 meters per second. Always. This broke physics. It didn't make sense. How can the speed of a beam of light be the same whether you are standing still or chasing it in a supersonic jet? Enter Albert Einstein. In 1905, he looked at this problem and realized that if the speed of light is absolute and unchangeable, then something else has to give. If speed equals distance divided by time, and the speed of light cannot change, then distance and time must change instead. Let's visualize the most famous thought experiment in history, the light clock. Imagine a specialized clock consisting of two mirrors facing each other, one on the bottom and one on the top. A single particle of light, a photon, bounces up and down between these mirrors. Tick-tock, tick-tock. Every time the photon hits the bottom mirror, 1 second passes. Now, place this clock on the ground next to you. You watch the photon go straight up and straight down. The path is a simple vertical line. Next, imagine we put an identical clock on a super-fast spaceship flying past you. You're watching from the ground. As the spaceship zooms by, you watch its clock. But the spaceship is moving sideways, so from your perspective on the ground, the photon inside that moving clock isn't just going up and down. It has to travel diagonally to keep up with the moving mirrors. It moves in a zigzag pattern, up right, down right, up right. Here's the kicker. A diagonal line is longer than a vertical line. We know from geometry that the hypotenuse of a triangle is longer than the vertical side. So the photon on the moving ship has to travel a longer distance to complete one tick than the photon in your stationary clock. Now remember the golden rule. The speed of light is constant. It cannot speed up to cover that extra distance. It travels at the exact same speed as the photon sitting next to you.
If the moving photon has to cover a longer distance, but it's traveling at the same speed, it simply takes longer to get there. This means the tick on the moving clock takes longer to happen than the tick on your stationary clock. The moving clock literally ticks slower. Time on that spaceship has slowed down relative to you. This is special relativity. It's not that the clock is broken. It's not a mechanical error. It is a fundamental property of the universe. In order to keep the speed of light constant, time itself must slow down for moving objects. Now, you might be thinking, okay, but how much does it slow down? I drive my car every day and my watch doesn't go out of sync. You're right. At everyday speeds, even in a jet fighter, the effect is incredibly tiny. We're talking about fractions of a nanosecond. That's why we never notice it in our daily lives. We are essentially crawling through the universe. But as you get closer to that universal speed limit, the effects become dramatic. Let's look at the famous twin paradox. Imagine two identical twins, Alice and Bob, both 20 years old. Bob stays on Earth to work at mission control. Alice becomes an astronaut. She boards a spaceship capable of traveling at 99.5% of the speed of light. Alice sets off on a journey to a distant star. From Bob's perspective on Earth, Alice is moving incredibly fast. He looks through his telescope, hypothetically, at the clock on her ship. He sees her clock ticking in slow motion. He sees Alice moving in slow motion. Even her heartbeat would appear slowed down to him. To Bob, the journey takes 10 years. He waits, ages, and eventually Alice returns. Bob is now 30 years old. He's got gray hairs starting to show. He's lived a decade of life. But when Alice steps out of the spaceship, she is 21. For Alice, the journey didn't take 10 years. Because she was moving so fast, space compressed and time dilated. To her, the trip only took 1 year. She experienced just 1 year of thoughts, 1 year of meals, 1 year of sleep. This is where it gets really trippy. Alice didn't feel slow. Inside the ship, everything felt normal to her. If she poured a cup of coffee, it poured at a normal speed. If she watched a movie, the actors spoke at a normal pace. It was only when she reunited with Bob that the difference became real. She has effectively traveled into the future, Bob's future. This brings us to a deeper, more philosophical way to understand it. It's a concept that helps everything click into place. Imagine you are in a car, driving across a flat, open desert. You are driving at a constant speed of 60 miles per hour. If you drive strictly north, you are making maximum progress toward the north. Your speed toward the east is 0. But if you turn the steering wheel and start driving northeast, you are now splitting your speed. You are making some progress north and some progress east. However, because your total speed is limited to 60 miles per hour, your progress toward the north must decrease. The more you travel east, the slower you travel north. Physics tells us that we are all moving through a 4-dimensional environment called space-time. Just like the car in the desert, you are always moving through space-time at a constant speed, the speed of light. But most of that motion is happening in the time direction.
Right now, sitting in your chair, you are traveling through time at maximum speed. You are hurtling toward tomorrow as fast as possible. Your motion through space is nearly 0. But when you stand up and start moving through space, you have to divert some of that velocity. You have to turn the steering wheel of your existence. Because you are now using some of your speed to move through space, you have less speed available to move through time. The faster you move through space, the slower you move through time. If you could reach the speed of light, maximum motion through space, your motion through time would drop to 0. Time would stop completely. For a photon of light, time does not exist. From the moment a photon is created in a star to the moment it hits your eye 1 million years later, 0 time has passed for that photon. It is
instant. So, is this all just math on a chalkboard? Do we have proof? Absolutely. We rely on it every single day. If you have ever used the GPS on your phone to find a coffee shop, you have relied on general and special relativity. The GPS satellites orbiting the Earth are moving fast, about 14,000 kilometers per hour. According to special relativity, because they are moving fast, their onboard atomic clocks tick slower than clocks on the ground by about 7 microseconds per day. However, they are also further away from Earth's gravity, which speeds time up, a story for another video, which adds about 45 microseconds a day. When you combine the math, the clocks on the satellites drift by about 38 microseconds every single day, compared to us. That sounds like nothing, but light travels incredibly fast. If the engineers didn't program the satellites to compensate for this time dilation, if they assumed time was the same everywhere, the GPS accuracy would drift by about 10 kilometers every day. Within a few days, your map would say you are in the middle of the ocean when you are actually in your driveway. The system would be useless. We also see this with subatomic particles called muons. Muons are created when cosmic rays hit the top of Earth's atmosphere. They are unstable and decay incredibly quickly. In a lab, a stationary muon lives for only 2.2 microseconds before it falls apart. Even if they traveled at the speed of light, 2.2 microseconds isn't enough time to reach the ground from the upper atmosphere. They should all decay long before they hit the surface. So, what does this actually mean for us? It means that now is a relative concept. My now and your now are not necessarily the same if we are moving at different speeds. It suggests that the separation between past, present, and future is not as rigid as we think. It also hints at the limits of our reach. Because time slows down as we approach light speed, human interstellar travel is theoretically possible within a human lifetime. If we could build a ship that travels at 99.9% light speed, we could reach the center of the galaxy in just 20 years of ship time. The catch: 30,000 years would have passed on Earth. We could explore the universe, but we could never come home to the people we left behind. We live in a universe where speed is the currency we pay to slow down the clock. We are all time travelers, usually just drifting forward at the standard rate. But physics has given us the recipe to change that rate. We just need the engine to do it. So, the next time you feel like time is slipping away too fast, remember, strictly speaking, if you want to make it last longer, you just need to move faster.